Hello, everybody. Welcome to Gabversity, where facts don't care about your feelings. And as Pompous says, you can go fact yourself. And now let's talk about some ads. I just came back from the Gabsmacked channel where remaining silent is not an option. All right. And on Gabsmacked, I give updates about what's happening in the Middle East because I watch Arabic news and I get Arabic Twitter feeds. And if you want to know more about those, you can go to my Twitter, which is the handle is @anautist, ANAUTIST. And I retweet some things from the secular Lebanese army, and you can hit translate on a PC or whatever on a Mac. You can translate it into English, and it's only little tweets, so you can get a rough idea of what's happening and where I get my information from. So you know that I'm citing my references, which is not what not what fake news does. Real news cites its references, right? It's got to be verifiable. Even if it's not true, it has to be verifiably not true, as opposed to, trust me, an anonymous source told me something. No, that doesn't fly with me. All right, the Dome Father is creating a new site for Gabsmacked and Gabversity. It's called, I'm calling it the Gab Initiative. And the Gab Initiative is going to take from all our 3 different channels. It's going to take from Gabsmacked, where remaining silent is not an option, and Gabversity, where facts don't care about your feelings, and Sixlang, where we learn 6 languages. It's going to take all of those and it's going to archive them in an amazing thing called the Gab Initiative. And basically, you'll just have to, like, our members on Patreon get a lot of those for free. But if you're not a member of Patreon, then you just pay to have to watch the replays and stuff like that. Yeah, they'll all be archived. They're all in beautiful locations. And so, a really massive thank you to the Dome Father. And then pretty soon we're going to be doing some coffee mugs with Pompous. It's going to have Pompous on the front, and it's going to be "Go fact yourself, bitches." So that's going to be one of our coffee mugs. The other one's just going to be the thumbs up with Gabsmacked. Gabsmacked, remaining silent is not an option. So there'll be our 2 coffee mugs that are coming out. But there's a lot of stuff going on, and it's just crazy. All right, those are all our advertisements. Now, did you see that my message? Absolutely, it actually came from you, my dear. We owe the original idea to Nelly Bell. And I responded actually to that whole message you sent me, the whole argument about vaccinations. I made a whole a speech on that at Gabsmacked under the VIP. I think I did it I think I did it on Monday or last Saturday, one or the other, I don't remember. Anyway, that's all our ads. So now we're going to move into the infinite square world about mugs. Yes, I did. I responded about the mugs as well. Okay, so what I'm going to do is we're going to learn all these topics, Patriots United, yeah. And I'm going to do the problems at the end. So we'll probably do about 20 problems at the end, which will encompass all of these topics for Chapter 2 of Introduction to Quantum Mechanics by Griffiths, 2nd edition, which you can get for free off the net. Just type in Griffiths, 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 Intro to Quantum Mechanics, 2nd edition, PDF. If you enter that in, you'll find to get the PDF. As long as you do it legally, like, you know, I get mine legally. I pay for them, and sometimes you can get free stuff because I'm a member of certain sites and stuff. All right, we're going to talk today about I received no reply about mugs. I replied it on my Gabsmacked actually talking. It was like a 3-minute video that I made, and I think it was called something like driving buses, Scott, hypnosis, and answering vaccinations or something. All right. So now we're going to talk about the infinite square world. Now, the reason is this. Let's say that Nelly Bell is walking in a park and there is a well, right? And the well is only 1 foot deep. So she didn't see it. She's like, whoa. And she falls into the well. Now, she'll be startled. But after recovering, you know, Lord willing, and she's fine, she'll just climb out of the well and continue. Okay? So now, imagine Nelly Bell is the quantum particle. So the quantum particle, she's walking around, she falls into the well, we've captured the particle. But the particle gets away and then disappears again, right? So how do we capture the particle so that it can never get away? Well, the way to do that is to create an infinite square well. And that means that Nelly falls in, she just keeps falling down the well. And that way she can never get out. So obviously, that type of world does not exist, okay, in real life. But mathematically, we can recreate this type of world. Why, Boogie Bumper, do we want to, and BB Retrievers, why do we want to make an infinite square well? I try to be busy, my friends, yeah. I still got to go do gym after that shower, and then I'll do astronomy later on. Don't forget, guys, patreon.com/Gabsmacked. Yeah. Become a member, $1 Australian a month, and you'll get heaps of private videos. Got to run yourself. Run. All right, brother, all the best. Mr. Meme Machine of the Week. All right, so mathematically, why are we reconstructing an infinite well? The reason is because it's a very, very easy way to understand the concept, and you would fall through to China. Did you guys know, what time is it there? It is 1:35 p.m. on Tuesday. Is it Tuesday or Wednesday today? I don't even know. Mom, are you there? Is today Tuesday or Wednesday? Sorry? Wednesday. All right, it's Wednesday today. Oh, yeah, okay, Tuesday, yeah. Tuesday, all right, we're Wednesday, yeah. 8:30, California. That's probably why I always get the Californians in our afternoon because everyone else is asleep. It's probably like, yeah, 11:30, there you go. So you're on the East Coast, yeah. It's funny, like, I always get East Coast audiences, I get either really early morning for us or really late. Yeah, 5:30 a.m. here. Jeez, 5:30 a.m. You must be in like Israel or something. 5:30. Hold on a sec. No, that's not right. 5, 4, 8 hours. You're probably in Greece or Turkey or Italy, the Netherlands. Okay, there you go. 2 scopes back here with 6 p.m. Scope o'clock. We now time ourselves with scopes. All right, so now let's get back to physics. Okay, why is this done? Because it mathematically makes things easy, and I'll show you what I mean. All right, what we're going to do, and I'm going to come back to IQ, dinner with Gab. Hey, that's called Gab dinner or Ginner, I don't know. All right, so let's do it. Okay, here we go. So let's say we have, right, the average IQ is 100, okay? And here is the distribution. So you have people who are really smart up here, and now it's windy again. Gotta be careful. Come on, focus. There we go. If I put my finger there, it focuses. All right. So here we have geniuses. Okay, and then somewhere it cuts off. In other words, there's no human above this level. There's some level, like Dr. Hawking, you know, Gabsmack, I don't know, whatever. That was me being funny. All right, and here you've got really, really, really retarded people like my auntie, who's actually really, really, she suffered a lot of brain damage, and so she's a retarded savant. And beyond that, there's no humans, right? And then here is where most humans are. Okay. Most humans are in what we call the standard deviation, where I am on that one. Well, you're very funny, so you're probably very smart. All right, so this is the standard deviation. Okay, it looks like an angry person, actually. There's the eyes and there's an all right, and most people live around here. Now, the thing about the particle is this wave goes forever. So the particle the wave goes like that for eternity, right? So you could never really find a particle because it might be on the other side of the universe. So what we do is mathematically we create an infinite well, and we trap the wave in here. Now the wave comes across, and when it falls in here, it's like, whoa, and it becomes a particle. Okay. So that means that we only have to look inside this well. That's what we're saying for the particle, which is really good, because then instead of doing the integral from minus infinity to infinity, which would make things very difficult, now for this, we just do the integral from minus x to x. And here is x, right? And here is minus x. And here is 0. So minus x and x. So we now can only do integral from minus x to x. So it makes the maths a lot easier. So here is the potential, right? And the potential of its location, right? In other words, the energy packet. V of x, and it works like this. This is what it looks like mathematically. I'm just repeating what I was doing here, but I'm putting it into mathematical form. Okay, so it is 0 if minus x is less than 0 less than x, okay, and less or equal to, and infinity otherwise. Alright, so v of x equals, so v of x is the potential of the particle. The potential energy of the particle is either 0 inside or infinity otherwise. Okay, so inside it's 0, which means it exists, and outside it's infinity, which means it does not exist. Okay, that's all we've done. Okay, so now what I'm going to show you. Hey, so what I'm going to show you now is that outside the well, right, we say that psi of x equals 0. Psi of x equals 0. So you remember from before, the little psi of x, which is the space equation, the space section of the equation. It equals 0. And what that means is that the probability of finding the particle is 0. Okay? So it's like when you lost your phone. If your phone is 100% in your house, then the chance of finding it outside your house is 0. That's what we're saying. Okay? So where are we? Okay. So then, if the chance of finding it is 0, then the wave looks like this, which is a classic harmonic oscillation. Classic harmonic oscillation is a very, very standard mathematical equation that actually maps onto huge amounts of things in the world. So I'll give you an example. The harmonic oscillation equation, classical harmonic oscillation equation, actually does this. It maps suspension in your car, this vast knowledge. Good question. I am a savant, which means that part of my brain has an IQ so high that it can't even be measured because there's no one to compare it against. There's only 2 people in the world, me and another guy, who have that ability in this form. There are a few others, there's like 5 or 6 people in the world in total. And I was reading novels by age 3, and by age 10 I'd read all of the Encyclopedia Britannica, and I can read at about 11 seconds per page if I'm reading slowly. If I read fast, it's 6 seconds a page. And so my brain is able to suck things in and remember them. And are you serious? Yeah, there's a book about it. We need another 225 pre-orders. Yeah. All right. And thank you for asking. All right, so that equation, right, it maps onto the swaying of trees. The swaying of trees. The swaying of a bridge in the wind. The swaying of trees in the wind. Thank you, and thank you to you. I love to see you. It's not all good, by the way. It's very bad in a lot of respects. If you go to my other channel, Gabsmacked, or you go to YouTube, Gabsmacked, you can see all my autism videos, and you'll see there's a lot of bad stuff that comes with it. The harmonic oscillation would love to hire you, probably, but I'm not good at being told what to do. So, where are we? The swaying of trees. When a car goes over a speed hump and the suspension wobbles, if you have a bridge that's hanging in the wind and it blows in the wind, the Golden Gate Bridge, when there's an earthquake, for example, if there's an earthquake and the bridge shakes, or if there's wind and the bridge shakes, right? All of that is mapped with one unique equation. Now, I'm going to tell you the equation. You ready? Let's do it. The equation is this. Okay. Simple. Harmonic. Am I still inside the well? Yeah, you're trapped, my dear. Simple harmonic. I love that. Am I still trapped? It's funny. Simple harmonic oscillator equation. Okay. 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 So here it is. Psi of x. Okay. Psi of x, which is the wave equation, just the spatial version, holy crap, there's some sort of plane going around here. All right, equals some number by the sine, which is that's a trigonometric function of kx, and k is also another number, and x is the position of the particle, plus b cos kx, which is that k is the same and the x is also the position of the particle, and that creates the harmonic oscillator equation. And there it is, right there. Okay, there it is. Now, there's something hidden in this equation. What's hidden is that a and b, right, are made up of complex numbers. And complex numbers are numbers that are multidimensional. And in fact, Dr. Hawking uses those numbers to show mathematically that there are other alternate timelines, which in mathematics we can see exist, but we can't prove it. But it's almost a certainty that, I would say mathematically, logic tells us that it's almost a certainty that there are an infinite amount of multiple universes that run on different timelines. Yeah, and it's weird because those alternate numbers, they always appear in the swaying of things. So when you have, as I said, if you have a spring, pull the spring down and pull it up and it goes like this, right? That's that equation. If you get a tree and bend it and then it springs back and it does this for a bit, that's the equation. If you have a boxing bag and you punch it and then it swings back, that's the equation. Trying to think what else. Boom. The echoing of an explosion. So if there's a bomb that goes off and then you hear, hey, Tamara. Also, that is of that equation, right? All that repeated harmonic motion, right? The swinging of a pendulum in the clock skips and reappears as you go upwards or different. Ah, good question. It's the same equation, but it has different numbers. So what happens is this number and this number change. So if it's the same wave, but you're moving up levels, then the A and the B change. If it's a different type of wave, in other words, it's a different quantum particle, so instead of a light particle, it's a Higgs boson particle, right? Then the K changes. The K changes. So the K in that equation is the type of wave, and the A's and B's is the level of the wave, right? So I'll give you an example. My voice and your voice and everyone's voice is made up of those waves, the craziest of particles. My voice, your voice is made up of those waves, right? If I increase the volume of my voice, you still know it's my voice, right? That's because the waves haven't changed, but they've moved up and down. So if it's my voice, but I've gone louder or softer, this is what's changing. What's changing is the A and the B, but the K stays the same. Yeah, I thought you would. I thought you'd get that. Yeah, that's awesome. You got it pretty damn quick. Amplitude, Captain Deltron. Captain Deltron knows his stuff. Amplitude. That's right. It's not just amplitude, but amplitude is a subset of those two constants. It's exactly right. Yes. But if it's your voice instead of my voice, then the K changes as well as the A and B is. That's right. So now you know. So every single person in the world has a special K. All right. Everyone has a unique K to their voice. So mathematically, you could recreate someone's voice if you find the right K, which is pretty crazy. And you know, people have created computer algorithms to do that, or thought. Hey, Malitza Sada, my favorite Maronite is back. Alrighty, so I was just talking about the Maronites. Ah, you found it, awesome. Yeah, the one where I was talking about Hezbollah on Gabsmacked. Alrighty, so now let's move on. Okay, so now I can't comment on Gabsmacked, fascinating stuff. Ah, awesome. Well, always a pleasure to have you. Okay, so let's get back to what we were doing. Here, it's scary, it can be recreated. Yeah, absolutely. Well, if it can be created once, it can be created again. All right, so now we're coming back to Nelly Bell. Melitza. All right. So this is what we want for continuity. Continuity, what we want is we want the function to equal 0 at the boundary and at the center. That just means, mathematically, that means that when you have a skipping rope, obviously the skipping rope is all continued. Otherwise, if you do this, half of it's not moving, right? So if you don't have a continuous wave function, then you can't find the particle. Math is so sexy. I'm down in his well. All right. Okay, so where are we? K equals 0 is no good because it will imply that equals 0. Negative solutions give nothing new, and we can absorb the minus sign to A, so distinct solutions are these. All right, so outside of the well, so Nelly is fallen into the well, right? Now, because she's fallen into the infinitely deep well, she can't get out. But memories of her of outside still exist, because as she's walking around, people remember Nelly from outside the well. So her memories still exist, but you won't find her, right? And that is what happens to the particle. The particle falls into the well, but the wave function still exists outside the well. So all the potential fucking flies, all the potentials of where the particle can exist still is outside the well. In other words, the particle could be here if we were able to get enough energy to get it out of the well and put it here, right? So what that means is that Nelly could be in these woods, Nelly could live in that house, Nelly could be walking down the street, right? All of these are possible, okay? So that is what that equation is trying to say, okay? And all the possible locations that where she can be gives us what K is, and I'll show you what K is, okay? K outside the well is this, behind you. All right, K is this. Someone kill this fly. K N equals, these are multiples of K. Do we ever die? Well, that's, being alive I think is an illusion, but because basically we're actually, our consciousness is aware of us after we've died and the new version lives. So, you know, we're sort of living in the past. K N equals N pi over A. Because we are made up of energy. Yeah, that's right. So we don't, because the particles that made us up existed in other things before we were born and will exist in other things after we die. So we're always going to be around, as long as the universe is anyway. We're just not conscious of it. Okay, so now Nelly Bell, thank you, I try to. Nelly Bell is now going to try and get out of this infinitely high well. So she's at the bottom now, which nobody knows what happens when we die. This is true. So only I am a wave. The memories of you outside are a wave. Inside you're a particle. So inside you're actually there going, get me out, and you're trying to climb up and get out. But you can't. But what happens is that each time you jump to try and get up, right, you exert energy. Right? So imagine that's what we're going to look at in this particle now. So this is the original. This is when you're relaxing, fat and virgin. When you're here, that's the ground state. This is the next level up. This is getting excited. This is getting really excited. Get me out, get me out. And that's not a dirty joke, by the way. All right. Okay, here's something interesting. The N, send me a trampoline. You are not smart. Get me out. Don't try. All right, so what we have here is certain energy states, okay? And what that means is that the particle can only physically exist, and this is to answer Queen Notifa, it can only physically exist at certain levels inside the well. Just like at a traffic light, the light can only be on the green, on the orange, on the red. It doesn't exist in between, and that's how we are at that level. And here is the equation, right, for the energy levels. So psi n of x, Okay, psi n, so these are the energy levels. Energy level 1, n represents the level, so n is 1, 2, 3, 4, 5, right? Equals the square root of 2 over a sine n pi over a x. So there's your next equation that we're going to use in some of the problems. Particle man, 8 triangle man. And we kill the fly. Got him! Bugger. Got the bastard. Okay. Be awesome. What's interesting is that if you're at the bottom of an infinite well, you can never get out. If you're at the top of the infinite well, you'll never get to the bottom. It's a very unusual concept. Okay, so we know. Can you spot the point at which it fails? All right, so we have the Kronecker delta. Should I explain that to you? No, not really. I will explain that these equations are mutually orthogonal. Each successive state has one more node, zero crossing, has none at the ends that don't count. Yeah, so they are mutually orthogonal. Yeah, they are linearly independent. All right, that's more heavy mathematics. I won't waste your time with that. They are complete in the sense that any other function can be expressed as a linear combination of them. Yep, that's pretty cool. I won't bother you with that. That's something I'll do myself. Next, I'm not about to prove the completeness of the functions, but if you studied advanced calculus, you'll recognize the equation nothing more than the Fourier series for fx. All right, yeah, you haven't done this. So basically what they're saying is that you can create waves with other waves. Right, so what that means is that, like for example, my voice is made up of independent waves, and all those waves added together makes my voice. It's the same with when you make colors. Blue and yellow make green, but I think blue and yellow are fundamental colors. So you can't, yellow was not made up of blue. Blue and yellow are independent and they make green. And it's the same with quantum particles. Okay. The second is universal regardless shape potential. Orthogonality is quite general. I'll show you a proof. I'm afraid most things simply assume completeness and hope for the best. Stationary states are evidently this. Okay, so most general solution to the time event is a linear combination of stationary states. All right, so here, where are we? I'm trying to make it a little bit easier for everyone here. The completeness of the psi's confirmed in this case guarantees I can always express psi x0, and their orthonormality licenses the use of Fourier's trick to determine the actual coefficients. Okay, so here is an example. All right, let's make it easy. Let's start with an example. So we're now done with Nelly. Thank you for being our volunteer. You can now go home, and the infinite world was only a dream. You wake up, it's all good. Alrighty. So let's do it. Here is a function. The function, okay, is phi or psi of x0. Okay, this is the two-dimensional wave, and the wave is expressed by this: a x outside of a minus x, as long as 0 is less than or equal to x, less than or equal to a. So what this means is that in the well, right, here is 0, here is a, and the middle is x. Okay, so instead of minus x, and that was 0, we just made 0x and a. Same deal, right? The particle is in here, and the particle is like bouncing across left and right, right? The chance of finding the particle, right, is obviously the most at x, right? Because that's the average position of the particle. Right? come back, periscope, come back, you can do it, there we go. Okay, the least chance of finding it is here or here. So it's going to look something like that. That's the chance, that's the probability distribution. All right. So now I'm going to draw the wave for you to show you what's actually going on. So we have this, right? This is x distance. Okay. Here is psi of x0. Okay. So now what we're going to do is we're going to say here is 0, here is a, okay, and then we have the probability distribution, okay, which isn't, it's an inverse parabolic function if anyone's done mathematics here. All right, now we have a squared over 4, which is the maximum, okay, and this is where you'll find the particle, okay, and that's the wave function. So when the wave function, which is this one, right, when you have a squared over 4 and you put it up in here, then you will get the maximum position of the particle, and that's a frozen point in time. Outside of the well, right, outside of the well, the chance of finding it is 0, so we've locked it up. That's basically what we're done, and now I'm going to show you some mathematics around that, and then I will probably stop. So here is the solution. What we have to do is, our goal is to find all the missing numbers so that we can use this formula to actually find x instead of just having magic numbers everywhere. We have to find the unique numbers of a, b, and k. Hey, that's pretty cool. Well, let the Dome Father know if you want. I completed his link and I'm just waiting on the next link so I can read the link out to everyone from now on, and then I got to upload the videos there, so I've got to figure out how to do. All right. And then what I'm gonna do, this is all a new language for you. It actually is a new language, honestly. So it looks confusing, but if someone actually, like if I built you up over 2 years to teach you fundamentals of maths all the way up, you'd be able to do it. I don't think anyone, it's not as hard as it looks. It's like learning a language. Some people are better at it than others, but you can still learn it. Anyway, I really love it. I'll be hunting for your mug reply. Well, I'm definitely working on a mug, that's for sure, at the moment. And I'm going to work on buying them and making them in Australia so that I can ship them to you guys, and it will still be cheaper than if I did it in the US. Maybe I'll find like one person, one of you, it's like calc and stats mixed. Yes, that's a good one. Banter is fun. You successfully increase that fly's entropy. All right, Captain Deltron knows his stuff. He or she's got some very good knowledge there. It's a very good joke. Once I teach you guys entropy in physics. Actually, I have a channel called, in Gabsmacked, I have a subgroup called physics, and I gave a lecture on entropy. All right, let's figure out A. Is this quantum mechanics? It is. It is an introductory quantum mechanics course. All right. So here we go. Okay, let us begin. We have 1. We're going to normalize the equation, right? And I've done lectures on normalizing already, so go back and have a look at them. 1 equals the integral from 0 to a of the wave x0 dx, and we absolute value it or modulus it and square it. Okay, I've done this many times before, so I won't explain it again here. Then what we do is we put the wave function in, so which implies that 1 equals the integral from 0 to a, and let's put the actual equation in, right, which is a squared x squared a minus x all squared dx, right? And that's also absolute value, right? But I'm not putting it in because the values are all positive anyway. They told us in the question they're all positive, so that's fine. And that, right, which implies once you actually do the calculus, right, 1 equals absolute value of a squared oh sorry, a absolute value of a all squared, well, same deal anyway, a5 over 30, and so therefore, once you do a bit of algebra, a equals the square root of 30 over a5. Proven. Alright, so now we know what a is. So we go back to this original equation they gave us. We now know what big A is. We've solved it. It's actually root 30 over a to the 5. Okay. Now, what we want to do is find the nth coefficient. This is going to be interesting. So to find the nth coefficient, okay, the formula is this, Cn. And if you remember in my last lecture, we were creating that infinite series equation, and we had C as a constant, right? And we want to now find what that C is, this special number that will tell us more about the wave, the properties of the wave. All right. So the formula is that we have square root of 2 over a, okay, multiplied by the integral. This is called the Fourier series if anyone's done advanced maths at uni. It's a special series devised by another genius called Fourier, or Fourier. All right, and this way, oh, by the way, what we're doing now, this is how mobile phones, radio stations, all of these are able to separate waves. So you know every wave is made up of subsets of waves. This equation allows us to turn the waves on its side and then go into another dimension and split them all up, so we can see all the small waves that make up the big wave. And that's how a digital radio works. So if you're tuning to like 96.3 or whatever it is, right? It's actually taking the big radio wave, it's taking it out, turns it to its side, goes into the alternate dimension. Freaking hell. Jeez. All right. It goes into the alternate dimension, splits out all the waves, selects the 96.3, and then uses that to give you what's going on that station. So that's actually happening, and mathematics allows us to do that as humans. Otherwise, we wouldn't have digital radio. So it's pretty amazing, huh? All right. So here is the equation that allows us to do that. Okay, so integral 2 over a sine n pi over a x, okay, and then a, which is root 30 over 5, we already figured that one out. All right, and then the equation, the wave equation, which is x a minus x dx. Okay, that's so this is the Gab wave. The Gab wave. Yeah. All right, now if we solve this, we get this, which equals, right? Which equals, has two possible answers, which is exactly what you'd expect, right? It is 0, right? If n is even, and it is 8 root 15 n pi over n pi cubed if n is odd. Alright, so we know that this is the sum of the infinite series. Alright, so therefore, here is the whole equation, and then I'll show you. So therefore, now we've been able to figure out the whole wave equation, which is, right, this is the two-dimensional wave equation, xt equals, and it's a long equation, so let's do it. I'm going to have to use the smaller side of the pen. Okay, smaller side of the pen. Here we go. It is 30 over, here we go. 30 over a, all square rooted, right? That means square root, it's the same thing. Okay, and then 2 over pi, which is that awesome number, 3. Then we've got the sum to infinity of n equals 1, 3, 5, like so n is odd all the way to infinity, of 1 over n cubed sine n pi over ax, and then e, so times e to the minus I n squared pi squared h bar t over 2 by the mass by a squared. All right, so here is the whole equation. So I'll show you what this means. This equation breaks down for us the infinite sum of the parts of the final wave. All right. So now what that means is that when we want to look for a particle wave, we can break it down into its we turn it sideways. Infinity. But we did this before, right? I'll show you, if you remember, one example of that is this. Which part is the Gab frequency? Gabversity. All right, so for example, 2, sorry, that's, you can't see that. 2 is approximately equal to 1. That's approximately equal, right? 1 plus a half plus a quarter plus an 8 plus a 16th plus 1 over 32. Now, this actually goes for infinity. If I want to get actual 2, sorry, it's wind. If I want to get the exact number for 2, I have to do this for infinity. But if I add these together, I get about 1.9 something, right? And these are that's an infinite sum. It goes forever. So same deal here. This wave is made up of infinite amount of waves. Okay. So what we have done, okay. Okay. In the laboratory, you don't find a particle to be in a particular state. You measure some observable, and what you get is the number. As we'll see in chapter 3, that coefficient squared tells you the probability that a measurement of the energy would yield the value E. A competent measurement will always return one of the allowed values, hence the name. All right, and Cn squared is the probability of getting the particular value of the energy level. Interesting. Okay, so of course the sum of these probabilities should be 1. All right. So in other words, that number C that we figured out, right, which I'll show you, right, was here, right, this number C, right, which is made up of that side, right, if you add up the infinite amount of C's, right, you'll actually get, and you absolute value and square it, you'll get 1. In other words, that means that you have a 100% chance of finding the particle in that location. All right. That's about it. So I think I'm going to stop there, and I will probably do a bit more on my own because I'm pretty tired. And then I will talk to you guys about the harmonic oscillator later. So lovely to see all of you. And remember, Gabversity, where facts don't care about your feelings. And as Pompous says, go fact yourself, bitches. That's Pompous. All the best until next time. Oscillator, that's really good.